Okay, welcome to today's mini lecture. In today's class, we are going to address two of the final topics of gas laws. The first one is Dalton's laws of partial pressure, and then the second one is Graham's rate of effusion. So what I would like to do is just go through and first talk a little bit about Dalton's law, about Graham's law, and work a few problems for you. So Dalton's law of partial pressures basically says that the total pressure of a combination of gases is the sum of each gas has its own unique partial pressure, and all of these pressures are independent one from another. So if I say I have gas A right here and it has a partial pressure of 1, and I have gas B right here and it has a partial pressure of 2 in a container, then now they're independent of each other. They are now going to have a total pressure of 3. All right, so the formula that we use to do this is just P total is equal to P1 plus P2 plus P3 plus P4 plus etc., etc. So however many gases you have. So let's go through and do question number 1. It says the atmospheric pressure of a room is 1 atmosphere. The room contains nitrogen gas with a partial pressure of 0.05 atmospheres, oxygen gas with a partial pressure of 0.75 atmospheres, and it says, what is the partial pressure of the carbon dioxide gas? So guys, when I wrote this down, I kind of abbreviated a little bit. I put P, and then instead of writing total, I just put TOT. And then instead of writing P1, P2, P3, I put the actual symbol for each one of the gases. So the first one was nitrogen, and then the second one was oxygen, the third one was carbon dioxide. So guys, I just come back up here and substitute my numbers in. It said the total pressure in the room was 1. Then it said the nitrogen's pressure was 0.05. It said that the oxygen's pressure was 0.75. They did not give me my final carbon dioxide pressure. So to get that, I just add these two numbers together, which is 0.8, and I subtract that from a 1, and sure enough, my final answer is 0.2 atmospheres. It's that simple. It's usually not a lot of really in-depth math. It's something you can do very quickly and easily just in your head. All right, so let's do the next one just to make sure that we've got it. It says a metal tank contains 3 gases, oxygen, helium, and nitrogen. If the partial pressures of the 3 gases in the tank are 35 atmospheres of oxygen, 5 atmospheres of nitrogen, and 25 atmospheres of helium, what's the total? Again, all of them are individual. They are independent of each other, so therefore all you have to do is write them down. I put the oxygen, I put the nitrogen, I put the helium. I add all of them together to get the total. So just be careful when you're reading these and make sure that you can pick out which gas you're working with versus the total amount. All right, the next question, it is a little bit different, and it relates to the labs that we do in AP Chemistry. It says, a sample of CO2 gas was collected over water at 25 degrees Celsius. The final pressure was 99.8 kilopascals. It says the partial pressure of the water at 25 degrees is 2.45 kilopascals. What is the pressure of the gas? Excuse me. What is the pressure of the gas? So I'm going to say total pressure is going to be equal to, and then I have the partial pressure of the CO2 plus the partial pressure of the O2. So before I go through and I work this, I wanted to show you and share with you what there's the setup that they're using. So this is called a pneumatic trough, and basically all it is it's a plastic container. You put water into it. It has a little hose that goes in the side and then a small little hole at the bottom, and then you hook this end, the open end, to like a test tube or an Erlenmeyer flask, and then when the reaction is taking place, if gas is being produced, the gas will be pushed through here and it will bubble up right here. Well, if I wanted to do this, I wanted to collect this gas before I start the reaction, simply take a test Sorry, it's taking me so decently, right? All right, so the gas bubbles would go up this tube, and I would be able to that amount of gas. The thing about it is do you see how I'm bubbling it? Well, if you ever just a tiny little bit of condensation in this tube, the reason as the gas bubbles go, it will pick up tiny water vapor molecules that stick. Does that mean? That means that pressure that's in here, just the pressure collecting, is going to be the water gas. So what I want to do is on the original, back over here. Hold on just a second. There we go. See this now? So that our total pressure, the CO2, plus the minute in there. How much water? You can look at 25 degrees, 4, 5. I know that. The final total pressure was 90, and find, all I have to do is subtract it, 4, 90. Write this down. The pressure is 97. I like that. Know about Dalton's law. So what I would like to do next is, it's totally in lecture, so I'm going to put grams fusion. So if I was to put a gas in on this tube, right, it would is as the gas, small little hole, is to the other side, which it travels. The reason we don't say diffuse through a small, it's basically just open up the gas, having it go in a very specific. So you have a formula to get that in your really and truly, guys. Let's say that we take track person that we have. This 100-meter, challenge them to, all right, we get up there, we take off. Who's going to win? Track's probably not going to be one. I'm a little bit old. I'm carrying a probably 100 pounds. So a track person is carrying just a lot quicker than me. The molecules, the mass, fast they effuse, the slower they're going to move. Look at this. It says nitrogen gas, which will go from one side. Already done the math for you. There's 2 of them. That's 20. Carbon dioxide is light dioxide. In order from the lowest is the lowest to be the heaviest. Each one of these, the highest, so it's 60 or 6, and finally, and say, oh, the one there, the molar masses. Number 1, Dalton pressures are independent together to give you grams rate.